So I'll start recording. This is the April 23rd class, so it's a Thursday. And I'm going to start off by saying stuff like that now because it looks like there's an error going on. Oops, message admit. It looks like there's an error going on with the videos, the class videos that I've been posting to my courses. Nai has been bringing this to my attention, and then Kim brought it to my attention earlier today as well. And I went back and looked for myself, and sure enough, every single one of the videos that I have on the class website for the videos are all the same. I have no idea how that's happening. I'm putting up different videos each time, and somehow overnight, I think, not over last night, it seems like over several nights, when the system does its refresh, it just sort of changes them all to the same video. So the one video that we're seeing over and over again is not helpful, right? Like, cover more stuff. So I apologize for that. I am aware of it now, and my plan is to basically upload everything to YouTube and then send the links out for that privately, so that we don't have a file that's an issue. So I still have all those files, so it should not be hard for me to get or do. It will just take a little bit of time. I plan to work on that tonight. So I apologize for that. In the meantime, I hope you're all well. I've got, let's see, I've got your homework and your extra credit, I think with one exception, quiz, all in and graded. So your grades are as up to date as I can make them. The next thing that'll be put into your grades, aside from this upcoming homework and extra credit due Saturday, homework due Sunday, will be the test coming up a week from today. So I plan to go through some new content today, a little bit of new content on Tuesday, and then touch a review. And then we'll go into the test, and I'll send you guys an email about what sort of things you can expect for the test, what you guys can expect for the test, so that you know what you're going in for. Okay? Before I get started, are there any questions on anything you'd like to know a little bit more about as we get moving? Okay, well, for whatever questions you may have, the chat is always there and open, and we can always go through that. So I'm recording now. I'm going to share my screen with this amazing PowerPoint. You're gonna be like, how did he make that PowerPoint? I'm gonna be like, skills, just skills. Okay, so minimize this, annotate this, you know the drill. Okay, I'll put this down here for the time being. Okay, so we kind of left off with polar bonds before, and we're going to go into shapes of molecules. So just so you know, the arc that we're on currently, and I talk about this arc a lot, is we start with atoms, where the electrons are in atoms, and then we go from atoms to forming molecules, and what kinds of molecules we can form. And we use Lewis structures to represent those molecules, and those molecules, based on their Lewis structures, have shapes, and those molecules, based on their shapes, will have properties. Okay, so one of the things that we're going to be going over is their shapes and their polarity, which lends a lot to their properties. Properties is the last thing we're going to do, and we'll see that on Tuesday of next week. Okay, so as I showed you guys before, the number one example for showing a polar bond is hydrogen fluoride, and that is a very polar bond, so much so that we recognize part of it as being partially negative, the other part of it being partially positive. So we've got this net distribution of charge where we've got more electrons around the fluorine than the hydrogen. And that's because when this pairing comes together, they're not sharing their electrons equally. Fluorine has the electrons a little bit more often than the hydrogen does. As a result, a negative charge builds up around fluorine, and the hydrogen gets a positive charge built up around it. So electrically, it's neutral. It's just that there isn't the same charge everywhere it's distributed. So the distribution means I've got this like cloud of electrons that's just bigger around the fluorine and smaller around the hydrogen. This would look like a gel capsule or something if it was uniform distribution of electrons, but that's not the case. So this polar bond, and these two being the only two atoms in the molecule, make it a polar molecule. And the polar molecule is something that results from the net separation of charge that is due to polar bonds. And net separation is the thing that's important here. And the result of a net separation that does not come out to zero is what's called a dipole moment. Okay, so a dipole moment is something that exists in a molecule if there is a net distribution of charge in that molecule. So let's take a look at carbon dioxide here. The polarity of a bond is determined by the electronegativity of the two things in that bond. So carbon's on one side, oxygen's on the other. Between those two, oxygen is the more electronegative. So this oxygen is pulling electrons towards itself. Same thing on this side. This oxygen is more electronegative than this carbon, so it's pulling electrons towards itself. And it turns out that if both of these guys are pulling on electrons pretty equally, that means that there is no net pull in either direction. So there is no net buildup of charge on one side of this. So as a result, there's no net dipole. Water, on the other hand, because it's bent, we went through the shapes last time, because it's bent, oxygen is more electronegative. It pulls electrons up towards itself. Same thing on this side, up towards itself. So that means that there's a net dipole in the up direction. That is, this side of the molecule is more negative than this side. So there's a net dipole, which means that it is a polar molecule compared to carbon dioxide, which while it has two, polar bonds in it, there's no net dipole, making this a non-polar molecule. So how do we determine if something is polar or non-polar, which is the way questions like this would be asked, and there'll be a question like this on the next slide. Well, the way we do it is we draw the Lewis structure first. We determine its shape, something we learned how to do last time. And then we look at the bonds to see if there are electronegative atoms in those bonds. And we see if there's a net pull in some direction. So let's go to the next slide. And I've got these three molecules, CHCl2, CH2O, and CCl4. Carbon's going to be in a lot of these because it allows us to have just four things around a central atom. Coffee just cools down in a cup so much faster than anything with a lid. All right, so I've got these three things. So the first thing I do is I draw the Lewis structure for each, and this is what they look like. So carbon in the center, I've got two chlorines and two hydrogens. It looks like these chlorines on opposite sides. These hydrogens are on opposite sides. That's fine, I can draw it that way. CH2O, that's what that ends up looking like. Trigonal planar molecule. And then CCl4, here's a tetrahedral molecule where all of the atoms attached are chlorine. Okay, so I drew the Lewis structure, that's fine. When I draw or take into consideration what their shapes must be based on the Lewis structures, this is the shape that CH2Cl2 has. This is the shape that this has. It's the same as I drew it. And this is the shape that carbon tetrachloride has. Okay, so I know their shapes. Now let's take a look at like what bonds are electronegative here, or what atoms are electronegative, so what bonds might be polar. Well, this one's got two polar bonds in it because chlorine's more electronegative than carbon, and it's pulling electrons towards itself. Carbon and hydrogen, they effectively have the same electronegativity. So that means that there's no net distribution of charge there, which means that electrons are just being pulled in this direction. There's nothing countering that pull. Here, electrons are being pulled towards the oxygen. There's nothing countering that pull. So I've got a net dipole in this direction. Here I've got four, but they are sort of symmetrically distributed. So I've got one going straight up and then one going down and away, out and away, and in and away. So those four poles actually end up canceling each other out. There's no net dipole there. So trying to make the determination if these molecules are polar or not, this one's polar over here because it's got two poles that are harder than these other two poles. If this were a tug of war, this side would be winning. This molecule is polar because this oxygen is more electronegative. It's pulling electrons towards itself. This is polar over here, sorry, non-polar, because I've got four poles that are equal in just different directions. And they end up canceling each other out when we do sort of the vector math with it. Excuse me. Now, we don't do any actual math with this. There are ways that you can get at numbers for these things, and we don't do that in this class, but you can look at it visually and just sort of see. Now, the one thing I want to remind you of is the fact that as we get closer to fluorine on the periodic table, atoms get up more electronegative, with fluorine being the most. So just keep in mind that trend. All right, you can always look up numbers if you have to, but for the most part, the trend holds. And carbon and hydrogen, they have the same electronegativity. All right, so we would sort of pick up hydrogen from like over here on the periodic table and plop it down like over here. So carbon and hydrogen are effectively sharing their electrons equally. So if we take a look at two larger molecules like ethanol and soap, ethanol, you know, this wonderful thing that people love drinking and thinking they can dance, has two parts to it. It's got this tetrahedral carbon, this tetrahedral carbon, this bent oxygen. This part of it right here, there's no net pull of electrons. This part of it here, there is. Electrons are being pulled in this direction over here. For soap, it's a little different. I've got like a cartoon going here. So this has like a long hydrocarbon, a carbon and hydrogen trail. And then up here at the front, I've got like some polar end to it. So there are two ends to the same molecule. So it's just such a big, cumbersome molecule that we don't write out all the atoms. We just represent it like a cartoon. So this part of the molecule for ethanol is nonpolar, and this part right here is polar. As a result, this entire molecule is considered fairly polar. If this were getting longer, the nonpolar part would be so much bigger than the polar part that it would no longer be polar. For soap, the nonpolar part's really big, but the polar part's pretty big too. So what ends up happening here with soap is if you get something on your hands and it's like in any way oil-based, if you just throw water on it, nothing happens. Water just sort of beads up and rolls off. So what happens is this part of the molecule for soap interacts with water. This part of the molecule interacts with fats and greases and waxes and stuff, and basically wraps around them and rolls off into the drain with the rest of the water. So you need soap to get stuff off your hands. So wash your hands, use soap. Soap is amazing, especially with this virus. A virus is basically three things. You've got RNA, you've got proteins, and you've got like a lipid shell around the whole thing. And this soap disrupts the lipid shell, and then it's just RNA and proteins, and together those two are just RNA and proteins. They can't do anything. They need that lipid shell. So soap is one of your best friends in keeping yourself safe. Wash your hands, use soap. Okay, here's a picture of soap. Comes in lots of different varieties. It does that thing. And that's one of the reasons why we get some of this bubbling right here, because we get a lot of interactions that end up trapping air. And this is, again, the more cartoonish way of representing it. So here you have like some semblance of atoms. The black here is carbon, the white here is hydrogen. And it just goes on and on and on like this. And then here we've got some polar head. And so it's one of the ways that we talk about this. You see this in biology classes as well, the phospholipid bilayer of a membrane. So that's what they're talking about here. So you got the phospho group, which is very water loving, and then the lipid, which is very water hating, hydrophobic here, hydrophilic here. Those are words we'll make greater use of when we get together on Tuesday, but for the most part it holds. And I think it's something you're familiar with. Okay, so why is this important? All right, well, let's take a molecule like sugar. Sugar dissolves in water really easily. We know. One of the reasons we know this is because we can just do it. And one of the reasons we can do it is because this carbon atom has an oxygen on it. This carbon atom has an oxygen on it. There's no carbon atom here that does not have an oxygen on it somewhere. So this is a fairly polar molecule. So that when this polar molecule mixes with another polar molecule like water, we get a mixture. We get a homogeneous mixture. Okay, the sugar goes throughout it uniformly. This heptane, however, has no polar interactions in it, which means that throughout this molecule, electrons are being shared equally. So given the choice between interacting with a water molecule where there is a buildup of charge, or another heptane molecule where there is not, this molecule will choose to interact with other molecules like itself, as opposed to this one. So water is polar in both cases. Here, this is nonpolar. So if I put them together, there's no actual mixing that occurs. There's a separation between the two. And typically, this is less dense than water. And so this ends up floating on top, and water stays on bottom. So when like oil spills in the ocean, oil sits like a slick on top of the water, and there's water underneath. And the reason they don't mix is because of these hydrophobic, hydrophilic interactions. And then thermodynamically, it's because of entropy, really. Okay, so that begs the question, well, then why do white bears dissolve in water? Any ideas? Why would a white bear dissolve in water? Well, the reason a white bear would dissolve in water is because they're polar. Boom. It's a groaner, right? You're going to retell it. It's a good joke. You'll retell that joke. It's funny. Okay, so let me stop there for a quick second. See if there are this. For the quiz, can we see which questions we missed? I believe I can reopen those, and I may be able to do that for the as a study guide for the test. So I'll make a note of that. Quizzes. I don't know what that's about. Okay, other questions? Curlis had that one. So he was asking if quizzes can be open for the quiz to see what you got wrong. I think I should be able to do that. Any other questions? A major question you would be asked on a quiz or a test is, can you identify a polar and a nonpolar molecule? And the way you'd go about that is by getting a Lewis structure, determining the shape from the Lewis structure, and looking at the atoms themselves. If you can do those three things, you can determine whether or not a molecule is polar. Okay, so just fair warning, the next bit we're going to go into deals with molecular orbitals. It is a lot harder to wrap your head around this, and it's not because the concept itself is hard, it's just highly conceptual. And it's pretty far afield from what you guys would have learned about in basic chem, so this is something you probably have not seen much of yet. For those of you that are going to go on into organic chemistry, the first bit of stuff we're going to go into is really important, bond hybridization. You'll want to pay attention to that because you're going to see it again, okay? And then for some of the other stuff that's going to end up coming up, the linear combination of atomic orbitals, that's going to be at the end of what we go into next. That is really weird, and you're going to want to read about that. So I've got some slides in here that should help. Ready to go? All right. Stunning silence means yes. All right, so let me go back to sharing my screen, which I believe is this one. Okay. All right. So moving on, molecular orbitals. So one of the things we've been doing with Lewis structures is we count individual atoms with their electrons. And we pretend like those electrons belong to those atoms the entire time they're in that molecule. Well, that works when we're trying to draw things out on paper. However, that doesn't necessarily represent reality. And some different models have shown us that when electrons from atoms go into molecules, those atoms don't retain the same electrons. They move everywhere. Those electrons now belong to the molecule. They've been assimilated, like they're in the Borg or something. So let's take a look at what this actually means. Here is a carbon atom. Here is its electron configuration, helium 2s2, 2p2. These are the electrons that participate in bonds. And so when it comes time for carbon to form single bonds, 4 single bonds, what happens is here we've got the S and here we've got the 3 Ps. We did this much earlier on. Well, one of these S's can be promoted up to the p orbital. And then this S and these 3 Ps will hybridize. The spherical shape on the S and the dumbbell shape on the P, they will form a hybrid. And what will happen is their energy gets lower by a little, so it's a little higher than the S, but lower than the Ps. And we now have 4 equal sp3 hybridized orbitals. And they each have 1 electron. And that's how carbon is able to form 4 bonds. This is sort of like a cartoonish way of representing that. I've got another slide that'll show it a little bit better. But when these things come together, hydrogen atoms with a single S-shaped orbital are able to overlap with this to form their bond. And these spread out with the size that they have at 109.5 degrees. So the molecular orbital model does more to explain why this has its shape than really anything else. So to move on from that, here is an image from your text. Now, this is a place where you really do want to read your text. So read the textbook. This is a good place to read it. So here's our S-shaped orbital. Here are our 1, 2, 3 Ps. And when they hybridize, 4 orbitals come in. So 4 orbitals have to come out. These are now molecular orbitals. And they look like, one of these dumbbell things has been inflated a little bit, like this one side of it's bigger. Well, that's because it merged with this thing. And so we end up forming 4 different, 1, 2, 3, 4 different sp3 hybrid orbitals. That's the result of this. And when hydrogen comes in with its electrons, so remember each one of these purple hybrid orbitals has 1 electron in it. Hydrogen has its 1 electron, and so where they overlap is where the electrons are shared, and that is the bond. Okay, so we don't really, bonds aren't really sticks. Okay, bonds are really just these distances between this nucleus and this nucleus, and then distance is defined by the shape of this orbital. Now, this can also happen with double bonds. So again, here's the carbon atom, 2s2, 2p2. And I've got 2 electrons here, and I got 2 up here. So one of them is going to get promoted. Yay, promotion, corner office. And then this orbital will form a hybrid with not all 3 of them, but just 2 of them. Oh, left out. So this one and these 2, they end up getting hybridized together. And 3 orbitals will form a hybrid. So there are 3 hybrid orbitals now. And they form equal sp2 hybridized orbitals. And then they got this 1 electron right here in the p orbital. And that is what results in double bonds, or what double bonds come from. So in this model right here, I've got a carbon atom and a carbon atom, and there's 1 bond between them, and there's a second bond between them, which is these p orbitals overlapping. So this second bond are these p electrons. And then I've got a bond to the hydrogen and hydrogen out here. So if I'm showing like ethene, which is what this is, then we can see how that kind of happens. Now there's a better picture of it here. So this S-shaped orbital will hybridize with these 2 guys, and they'll form, these 3 different lobes. And the best way we can make these lobes spread out is by, having them take up the points of a triangle. So which is why we refer to these things as trigonal planar, okay, trigonal bipyramidal, that sort of thing. So this is trigonal. One of these electrons gets promoted, but the hybridization only occurs with 2 of these spots. So we've got these 3 hybrid orbitals. So again, this 1s will hybridize with these 2 p's. So we have an sp2, that's where the 2 comes from. And then you got 1 p by itself. And so the way you can represent that, remember we said that trigonal planar is planar, meaning everything's in a plane. So these 3 hybrid orbitals are all in one plane. So when oxygen comes to interact with it, it's got 1 electron here that it can donate, and another free electron here in a p-shaped orbital. So this electron that's in its p-shaped orbital can interact with this electron that's in its p-shaped orbital. And that interaction is the second of the 2 double bonds. There's also a distinction here, and I want to point it out so that you can see this sigma right here. That is the name for a kind of bond that exists between 2 atoms. So if we have the electrons in the bond between the atoms, it's called a sigma bond. If we have the electrons being shared between the atoms that's not between the atoms, they're above and below, or out of the plane, I should say, it's called a pi bond. All right, so there is, but in a double bond, there is 1 sigma and 1 pi bond. That's what every double bond is made of. Double bonds can come together in 2 different ways. So remember, there is like a px, a py, and a pz, right? So when py's come together, they do so like this. When pz's come together, they do so like this. When px's come together, they do so like this, okay? And if my hands are the the nuclei, and these fingers here represent like the orbitals that come together, they're between the nuclei. So when those 2 come together, they form a sigma bond. When these other ones come together, they can form a pi bond. So carbon can form 1 sigma and 2 pi bonds, and that would be a triple bond. Now, I'm not going to go into the triple bond. Your book will, but it's just the same sort of thing here. One of this electron will get promoted, and there'll be a hybridization between this S and one of the P's. So it would be SP. So there's SP, SP2, SP3. Okay. Now it gets into some stranger territory, but I think territory we can reasonably go to. The whole idea of molecular orbitals is that they are made up of linear combinations of atomic orbitals, LCAO. And this is actually graduate research. If you were to go to graduate school or participate in any research, you might see like one talk on this, because people are really interested in how electrons are arranged in molecules, because they're trying to make electronics smaller. So we need to know how electricity goes through these things. Now, two things you should remember. One is that atomic orbitals, they will combine to make molecular orbitals. So atoms with their electrons defined by orbitals will come together to make molecules with their electrons defined by orbitals. And these are different orbitals. Okay, so somewhere like an S comes in and forms an sp3, that kind of thing. Next, our orbitals are conserved. So if two orbitals come in, that means they make two new orbitals. So if two atomic orbitals come in, that means they make two molecular orbitals. All right, so if you can remember those two things, that might help you a little bit with trying to wrap your head around what's actually going on here. So let's say I've got these two S-shaped orbitals here, all right? And they both contain one electron. So these orbitals themselves are not shapes. They are not things. They are ideas. These are probability maps. So we take these two probabilities and add them together. There are two possible solutions that come out. One is that the electrons they're in phase, they interfere with each other constructively, and the electrons end up spending time between the two nuclei, and that is called our bond. That's our bonding molecular orbital. However, they could come together and be out of phase and end up canceling each other out. And so what happens is they get close together, but no bond forms. Electrons are effectively pushed in opposite directions. And that's called an anti-bonding molecular orbital. And this dashed line here represents a node. It's a place where there are a 0% chance of finding electrons. So there are no electrons between them. So again, two probabilities, a bonding orbital and an anti-bonding orbital. This would be called a sigma orbital. This would be called a sigma star. Now, if I've got two hydrogen atoms that are here, so here's my energy diagram. I've got an S-shaped orbital and an S-shaped orbital. I've got two electrons coming together. They form a bond, and that is the sigma orbital that we see down here. Actually, I don't see it. You might. That's the sigma orbital we see down here. And then if there are any more electrons, they would go up in here. But right now, they all fit in here. Molecular orbitals hold two electrons, just like atomic ones. So H2 is a molecule we're used to seeing. He2, for example, is not. So this has two orbitals. There are two electrons in each, so a total of 4. So 2 electrons can go into this sigma orbital, and 2 electrons can go into this sigma pi orbital, meaning that the bond between here, there's one bond and one anti-bond. Anti-bonds are a lot of energy. They tend not to hold all that well, which means that effectively He2 does not exist. This has a bond order of 0, and we would not expect to find it in nature, and we don't. So that leads us to something really kind of interesting. There are unpaired electrons in certain things, and if certain things have unpaired electrons, they are called paramagnetic. Now, that is a word you're going to want to know, paramagnetic. Things that are paramagnetic will respond to a magnetic field. So if I have a magnetic field around this thing, something that is paramagnetic will be attracted to it. An example of something that is paramagnetic on this page would be, well, there's nothing here paramagnetic. There are no unpaired electrons for this. Everything where all electrons are paired, so all paired electrons in orbitals, are called diamagnetic. And that is something that is repulsed by a magnetic field. So it pushes away from magnetic fields. The bulk of your bodies are diamagnetic, okay? And so there is a problem here. Lewis structure for oxygen. If you drew the Lewis structure for oxygen, O2, looks like this. I don't see any unpaired electrons here. 2, 4, 6, 8, 10, 12. 6 times 2 is 12. That's exactly how many valence electrons there are. They're all in octets, no unpaired electrons, therefore it's diamagnetic. That's what I would guess. Oxygen, O2, does not respond to magnetic field. However, If I line them up and do this molecular orbital stuff and put them into sigma and sigma stars and pi stars, I can see that I'm left with a pair of electrons here, one up here and one up here, that are not paired up. They're in their own orbitals, which means I have unpaired electrons. So that means it's paramagnetic. Well, what the heck? When we do molecular orbitals, for S-shaped orbitals, it looks like this. We went through that one. For P-shaped orbitals, it can look like this, or it can look like this. For boron, carbon, and nitrogen, it looks like this. And then for oxygen, fluorine, and neon, it looks like this over here. They flip, they just do. Just trust me on that. And so when we're building the one for oxygen, there should be 4 electrons here in these things. So 1, 2, 3, 4, 5, 6, 7, 8, because there should be 4 on this side, 4 on this side, 8 total. So 8 electrons leaves an unpaired couple of electrons right here. So again, this would predict that oxygen is paramagnetic. Sorry, diamagnetic. Yeah, paramagnetic. And that's difficult to understand. So let me stop sharing this and start sharing my screen. And I want to show you guys something different. So I'll cancel out of that, go into this, show you this. This video will be posted to my courses. I'll try and make this large. So this is a friend of mine. He does the chemistry demonstrations at Harvard. I didn't even know that job existed. It's awesome. It's awesome. But let me start playing it. So what he's doing here.
Take this oxygen gas, pass it through this copper coil that's immersed in liquid nitrogen. The liquid nitrogen will condense the oxygen into liquid oxygen, which will collect here in this pre-cooled dewar. We will then take the liquid nitrogen and pour it between the poles of this magnet.
Okay, so just to be clear, there is oxygen in air, and so he's taking compressed air, running it through liquid nitrogen, and then the oxygen in there actually boils off at a lower temperature, so at a higher temperature than nitrogen does, and so it will condense in here. So as we go through this, one of the things that we'll see is that a liquid starts coming out in this tube. So we'll watch a little bit of this. So that liquid that's coming out right there is oxygen, liquid oxygen. Incredibly dangerous stuff. You might be able to see at the bottom of your screen that it's kind of blue. You may have seen me play with liquid nitrogen before, and I play with it a fair amount. I'm always careful to make sure that I don't see any blue in there, because that would be liquid oxygen, and that's very reactive. There he is, just swirling it like it couldn't have possibly explode. Now he's got this magnet, and he's going to cool this magnet down with liquid nitrogen so it's nice and cold. This does a little something to the magnet's power, but we're still going to see what it does. If you went near this with a credit card, it would erase your entire credit history. And now what he's going to do is pour this oxygen between these 2 poles and watch what happens to the oxygen. It sticks between the poles. Okay, so nitrogen just sort of rolled off completely because it is diamagnetic. Oxygen, because it has lone pairs, it has lone electrons that are not paired, is paramagnetic. So oxygen is truly paramagnetic. And the theory that we use, this molecular orbital theory, shows that. So Lewis models, they do good, but eventually they run out of steam. So this is a good example of what's going on there. So let me just minimize that or get rid of that entirely, actually. Okay. And just go back and remind us here on this last slide that nitrogen here has no unpaired electrons. As a result, it ends up being diamagnetic. Oxygen has these unpaired electrons. It ends up being paramagnetic. And the only other paramagnetic thing on here is boron. Okay? So that is the bulk of it. Now, I strongly, strongly, strongly encourage reading the book on this portion because it's wordy, it's conceptual, you're going to want to wrap your heads around it. There are parts in your book where they go into hybridization with D-shaped orbitals. I do not stress that in this class. Obviously it happens, but it's nothing that I feel the need to go over. This is fairly conceptual stuff, so I try not to go broad with it. I try to go kind of deep and narrow into just a couple of areas. So, questions, concerns, violent objections from anybody on this? Okay, to restate a couple of things. Homework due Sunday, extra credit due Saturday, test on Thursday, a week from today. And thanks to a couple of people who are pretty observant of things, Nye and Kim, who pointed this out to me. All of my videos are the same. I'm aware of it, and I'll be fixing it from tonight till tomorrow. I know how to fix. I know what to do a good fix. I mentioned YouTube, so I'll do that. And all the videos will be changed into YouTube videos and then brought back down, and that should eliminate the problem. I'm sorry that problem is there. I have no idea that it's going there, but I'm grateful for those of you that found out about it and pointed it out to me so that it's not a problem for other people. Thank you. Okay, miss seeing you guys, really do. I hope you're all doing well. And if you have any other questions, I'll hang out, but other than that, we're done. So I will see you guys on Tuesday of next week, the last day of new content, and a little bit of review. Okay, thank you. Thank you, Nice. See you later. Bye, Sarah. Have a good day. Oh, thank you, Ann. Take care. Thank you, Kim, for helping point out the problem again, too. Okay. All right, I'm going to end the meeting here. Good luck, guys.